To escape Earth's gravity, a rocket needs to overcome the gravitational pull of the planet. The force of gravity decreases with distance, so as a rocket moves higher above the Earth's surface, the gravitational pull weakens. The escape velocity is the minimum velocity required for an object to break free from Earth's gravitational pull and not fall back to the surface. At the surface of the Earth, the escape velocity is approximately 11.2 km per second, or about 40,270 km per hour. This means that a rocket would need to attain this speed to completely escape Earth's gravity and move away from the planet indefinitely. However, it's important to note that achieving this velocity directly upwards from the surface is not a practical approach for launching a rocket. Instead, rockets typically follow a trajectory that allows them to reach orbit around the Earth. This trajectory involves launching vertically, then gradually pitching over to gain horizontal velocity and enter orbit. To reach orbit, a rocket needs to achieve what's known as orbital velocity. Orbital velocity is the speed required to maintain a stable orbit around the Earth. It is lower than the escape velocity because once a rocket reaches a certain velocity, it can enter a circular or elliptical orbit without additional propulsion. The orbital velocity depends on the altitude of the desired orbit. For a low Earth orbit, LEO, which is commonly used for satellites and space stations, the orbital velocity is approximately 7.8 km per second, or about 28,080 km per hour. As the altitude increases, the required velocity decreases. In summary, while the escape velocity from Earth's surface is approximately 11.2 km per second, or about 40,270 km per hour, rockets typically aim to reach orbital velocity to achieve a stable orbit around the Earth. The specific velocity required for a rocket depends on the mission objectives, altitude of the desired orbit, and other factors. Here are 20 interesting facts related to the topic of rocket velocity and escaping Earth's gravity. The concept of escape velocity was first introduced by German scientist Johannes Kepler in the early 17th century. The escape velocity from Earth's surface is approximately 11.2 km per second, or about 40,270 km per hour, as previously mentioned. Escape velocity is derived from the gravitational potential energy equation, which takes into account the mass and radius of the celestial body. The escape velocity from different celestial bodies varies based on their mass and radius. For example, the escape velocity from the Moon is much lower than Earth's escape velocity. The first human-made object to achieve escape velocity from Earth was the Soviet Union's Luna 1 spacecraft in 1959. The speed required to escape Earth's gravity is not solely dependent on velocity but also on the direction and trajectory of the rocket. Rockets use multiple stages to reach escape velocity and achieve their mission objectives. Each stage is jettisoned when its fuel is depleted. In 1961, Yuri Gagarin became the first human to reach escape velocity and orbit the Earth aboard the Vostok 1 spacecraft. The concept of reaching orbit is more important for most space missions than achieving escape velocity, since achieving a stable orbit allows satellites and spacecraft to remain in space for extended periods. Achieving escape velocity does not mean a rocket has left the influence of Earth's gravity entirely. Gravity's influence diminishes with distance, but it never fully disappears. The escape velocity from the surface of the Sun, known as solar escape velocity, is about 617.5 kilometers per second, or about 2,223,000 kilometers per hour. The Voyager 1 spacecraft, launched in 1977, is currently the farthest human-made object from Earth. However, it has not achieved escape velocity from the Sun's gravity. The escape velocity of an object depends on its mass as well. A more massive object requires higher velocity to escape a celestial body's gravity. The shape of a rocket's trajectory significantly affects the velocity required to escape Earth's gravity. Optimal trajectories are carefully calculated to conserve fuel and achieve the desired objectives. Rockets use a combination of solid rocket boosters and liquid rocket engines to generate the necessary thrust for ascent. The Space Shuttle, a reusable spacecraft used by NASA from 1981 to 2011, achieved orbit around Earth but did not reach escape velocity. The escape velocity of an object depends on the mass and radius of the celestial body it is trying to escape from. Smaller bodies with less mass have lower escape velocities. The concept of escape velocity is crucial in understanding how celestial bodies retain their atmospheres and how objects like comets can enter and exit a solar system. The escape velocity from Earth's gravity is the highest of all the planets in our solar system due to Earth's relatively large mass and radius. The study of escape velocities and orbital mechanics is essential for space exploration, satellite deployment, and interplanetary missions, as it helps scientists and engineers calculate the required energy and trajectory for successful missions. These facts offer a glimpse into the fascinating world of rocket science and the principles involved in escaping Earth's gravity. In conclusion, escaping Earth's gravity is a complex and challenging task in the realm of space exploration. The concept of escape velocity represents the minimum velocity required for a rocket or spacecraft to break free from Earth's gravitational pull. While the escape velocity from Earth's surface is approximately 11.2 km per second, or about 40,270 km per hour, rockets typically aim to achieve orbital velocity to enter a stable orbit around the Earth. Orbital velocity is lower than the escape velocity and varies based on the desired altitude of the orbit. Reaching and maintaining orbital velocity is crucial for most space missions, allowing satellites and spacecraft to remain in space for extended periods. The study of escape velocities and orbital mechanics plays a vital role in calculating the energy, trajectory, and mission requirements necessary to successfully navigate and explore space.